So we essentially just number exams, rooms, and time slots from 0 and have a timetable is just 2 integer arrays, very simple, storing the time slot index and the room index for each exam. So 2 arrays, it's all in the same place in memory, and they're extremely fast to create. And so because we have to create these new neighborhoods, timetables in each neighborhood quickly, and we also want to evaluate the constraints extremely quickly, data locality matters a lot. So where these things are in memory, how they're represented, dealing with processor cache, cache misses, when to reuse data versus making a copy. Sometimes you actually don't care about having several copies of your problem representation at once. It makes things a lot faster. And importantly, we really care about incremental computation. So all of this local search kind of at a high level seems really simple, but we really don't want to recompute constraints from scratch every time. So when you make a move, we're only making small changes. We're moving an exam from one time slot to another, or we're swapping 2 exams. Anything that's not in those time slots is really not getting affected too much. So we can make huge strides in only doing some small computation. And we also keep track of which exams are essentially most responsible for the violations of our constraints, so that when we are picking moves in the search, we can try to prioritize moving exams that are causing lots of constraint violations, which is heuristic, but tends to be pretty good at identifying how to find exams to move to make the schedule better. And so yeah, so we are able to produce usable schedules in about 10 or 15 minutes. Those are essentially as good as the schedules at UBC before 2009-ish. So as good as a human could do, given many weeks of time to make a schedule. And in a couple of hours, you can get essentially the best schedules that you can get at UBC. They get slightly better if you run it for longer, but that's enough to get the ones that are used for your exams. And that's it. Are there any more questions? Time complexity? Yeah, so it's local search. There are some completeness results that say that if I give you infinite time, I will find you the optimal solution to this problem. But it's all empirical. Like there's very little actually for local search and solution complexity. I mean, the problem itself is NP hard. If that means anything to you. Anyone else?
How come there are 5 totally different data sources for all the course data?
That's a very good question. Because bureaucracy, basically.
I'll just say, like, there's the SSC, and that should, in theory, have all the course and all the student IDs, right?
Yes. But then there's each department has, well, not all of the departments, but a lot of departments have their own data stores. And the SSC also has, the SSC is almost a union of this data. So like all of the course codes and stuff, it's a mixture. Like if you look into the SSC backend, there's like a lot of that course code stuff is still in there.
What language did you use to write it?
It's all in C++. Yeah, a little bit of the pre-processing is done in Python, but all of the heavy stuff is C++.
Why don't UBC standardize its data beforehand? Or as that course code to make variants, so why can't they in specific formats to that format?
Also a good question. We tried to get them to do that at the point we started this project, and essentially it would have taken UBC IT over a year to kind of have that project get spec'd out and assign a person to it and blah, blah, blah. And so I just did it in a week or something like that instead.
How was exam scheduling done before this system?
A very, very smart human being in classroom services would essentially look at the data and look at all the previous exam schedules from the year before that and make a schedule over about 6 weeks. I think she started at UBC in the 70s up to 2009.
So 2008 before it was all of our.
Yeah.
So she's too young.
Yeah, thankfully, yes. Yeah, and she's like brilliant. Like the amount of work that she puts into making your schedules good is unreal. Like the women's studies courses in the evening that have evening exams often are closer to the bus loop. That's her. Hebrew, Arabic exams, like she takes the Shabbat into account. Like it's really intense how much work she puts into the exam schedule.
Did she have the input into this already?
Yeah, yeah, we worked really closely with her actually.
Is there any chance that this exam scheduling program may be open source in the future?
Yes, I want to say yes. There's a little bit of like IP clearance with UBC that has to happen, but yeah, we're working on it essentially. Yeah, I mean, you can find, there's a free one called CTT that's really good, that's available. It doesn't have all of the constraints I mentioned, but it's still pretty good. Yeah, I guess probably one more.
About, you mentioned about we need to clear the students' data with students' name, but why can't we just use UBC ID so that the student does that? So the UBC ID specifically
Yeah,
one student.
yeah, that's what it uses in the end, but we needed to give the data back to them with all of this, so it was a parsing problem, that was it. But it's just interesting to note that it exists like that at UBC. Oh yeah, yeah, absolutely. Yeah, it's not even just using that as a key, but the fact that you have to interact with it at all, you have to start worrying about this problem.
All right, thank you. Let's thank Chris. Thank you. All right. We have 10 minutes left. I'd hope to have longer, but that's fine. Okay, midterm, you can bring whatever sheet of paper into it, look at the web page. There's a practice midterm. There is a solutions to both assignments. There's a solution to the practice midterm. Does anyone have any questions about anything? Yes? Sorry? Yeah, it says you can use whatever you like on the sheet of paper. Yeah, you can write on every side. You can write wherever you want, write poems, do anything you want with it. Any other? You can do whatever you want. Write poetry on it, anything, right? I'm not going to check. Any other questions? People at one stage decided they should just put the whole book in very small font in it, but they actually decided that was a very bad idea. What?
What are the usual averages?
Oh, it averages about 6 pages.
Average grade?
Oh, I don't know. Yeah, you should be, if you can do this, you should be fine. I don't know. I don't know the answer to your question. I don't know what the average is. I don't think you should worry about it. All right. All right, let's, where am I going here? Okay. Let's, so what we did last time was we looked at this propositional data, this propositions and inference. So here's a summary of it. We did this last time. We did the bottom one. We did top-down proof procedures. Top-down proof procedures from the goal. We're going to use this to find a proof. So this, right. Top-down proof procedure searches from the goal to find a proof. I couldn't read it there. Okay, so that's what we did last time. We ended up looking at how this search procedure went, and at the end we looked at this, the search space for this particular query. So this is what we was writing on the board at the end of last time when everyone was trying to leave. The search space of a query queue, given a knowledge base, we have the nodes, or these answer clauses. The neighbors of the node, you select an atom in the body. Then there's a neighbor for every clause with that atom in the head. And the neighbors are defined by SLD, this SLD resolution, where we replace the element of the body of the answer clause with the body of the clause it's resolving by. The start node is just yes if my query, and our goal is just yes. So that's a summary of what we did at the end of last time. Are there any questions about that? Okay. So let's do a clicker question because we said we always would. Suppose the knowledge base consists of W if Y and Z, P if S and T, P if W. And we have an answer clause that says yes if W and R, and we've selected atom R. So we've selected atom W. So the question is, which of the following is the possible next answer clause? So which one of these is the next answer clause? A, yes if W and R. B, yes if Y and Z and R. C, yes if Y and Z and P. D, yes if W and R and Y and Z. Or E, none of the above. All right, does anyone need more time? Yay. Good. Let's do the next one. All right, suppose this the same knowledge base, but the answer clause is yes if P and R, and we're going to select atom P. And which of the following is the next answer clause in a proof? All right. How are we going? Anyone need more time? And the answer is A. A few people said, all right, people who said B or C, look at the definition again. Okay, we're just replacing one of them with one of the P's. You either choose the first clause or the second clause. Okay, are there any questions about that? All right, how am I going for time? All right. I wanted to do, Chris went much longer than I asked him to, but that was fine because it was interesting. So let's try and work out what to, I'll do an example of something. One of the things that we'll talk about next time is debugging programs. And one of the things that we can do when we're debugging programs is we can ask questions in here. So what we're going to do is, there's this funny program we're going to let you play with for the next assignment called AI log, which is designed to have a very simple version of this logic language to play with. And it has sort of fun, interesting things. The fact that we're having semantics within our system here. We can load, oh no, wait a minute. This is one I wanted to copy. Sorry. And this one here, we can actually ask a question. We can ask it questions. We can load things. We can ask a question. At the bottom here is L1 lit, and this is my intended interpretation. And it says, yes, the answer is lit. And now we have a sound proof, complete proof procedure. So what do we know if we get this answer that's our world that's not lit? What do we, and we know, and it can prove lit, what do we know? So if we can prove something that's not true, what do we know? Right, the knowledge, someone then said the knowledge base is buggy, right? Someone there said the knowledge base is buggy. right? So we have a bug in our knowledge base. But one of the things we'd like to do is, one of the advantages of talking about semantics is that we could think about why this knowledge base is buggy without knowing how it's computed. Because what we want to do is to use all sorts of fancy computing techniques to work out how to answer questions, but we'd like to be able to just use yes/no questions to actually produce what the answer is. And so if we ask this question here, we can ask how, and if you prove something, we've proved L1 is lit, there must be a clause with that as the head where the body is all proved. Right, so if we've proved L1 lit, here's what we use to prove it, light L1. Are all those three things true in the intended interpretation? Right, let's look. Is it light? Should live L1? Should there what? So 2 is wrong. Okay, and it can keep telling us why, and what's wrong here. Should W0 be live? So the body here, we're going to look at the body and we're going to say why is this one. So now we can keep going through live W0 if live W1. Is anything of both the elements of the body true or false? Okay, so what we're going to try and do is just when we have this, we can start asking questions about proofs, about how we prove things in here. Okay. And we can actually sort of use the semantics of this, the fact we know meanings of symbols, to actually work out how to do this. I've run out of time, so let's stop there, and on Monday we'll have the exam, and then I'll actually present this properly on next Wednesday.